All right, Dr. Robert Sungenis, welcome to Grimerica. Thanks for joining us.
So glad to be here. Thanks for inviting me.
Yeah, this will be interesting. Like, we were just chit chatting a little bit. We haven't really approached the subject from this angle before, but we've done lots of episodes on the solar system and different things like the electric universe theory and growing Earth theory and Simon Shack's I guess it would be binary system theory kind of thing, or the Tychos model. So I think this show will be a good complement. But I'm also not very versed with religion, Catholic stuff either. So we're a little bit we're a little green on that whole side of things. So thanks for joining us.
Yeah, well, I promise to make you white.
Yeah, you're gonna. So
who knows what color from that?
I mean, where do you want to start? I mean, you've got like Geocentrism 101, which is kind of where we want to end up, but maybe it's like a quick sort of background, a quick bit about how you started writing about this and debating people in the scientific field.
Yeah, well, to start out, I was a devout heliocentrist prior to the earthquake that happened in my life. So just to let you know, I know where everybody else is coming from. It's not like I was born this way. I was sitting home one Sunday in front of my computer, and I was futzing through the internet. Back in those days, it was a new thing, Now everybody's into the internet, but I was going through it, and this guy who had a PhD in astronomy, and he just died a couple of years ago. He's talking about the Earth being in the center of the universe and not moving. And I'm like, what? How can a PhD in astronomy be saying this kind of stuff? And so it was Sunday afternoon. I didn't have anything else to do for some reason, which is not usual. But I had to decide whether I was going to press the next key to get into his website, or I was going to go outside and play basketball. And I probably should have gone outside to play basketball, but I did press the key, got in there, read it for about 15, 20 minutes, and the guy knew what he was talking about. I could tell because I know the physics, and he knows the physics. And the physics allows it to be viable, a viable scientific theory. I mean, Einstein, I'll start with Newton. Newton had his F equals ma, and from him, the whole Copernican theory, heliocentric theory arose. Einstein had his theory. And so I guess the last, 21 years I've been doing this is a matter of showing the world in how many books? 12 books, probably 6 movies, a dozen or so lectures across the world, how you can defend the geocentric model. Not only with geometrics, as I was telling you in my email, because that's where Simon's coming from. It's all geometrics, but from dynamics, that is forces, because that's what F equals ma is. It's force equals mass times acceleration. So, after pressing that key, which was fate calling me, I responded, and been doing this for the last 21 years, defending something I thought I would never defend in 10 lifetimes, let alone one. And so here I am. Now, if you want me to give a sort of a 25-word or less reason why I think it's viable, I can do that. So that's the way to start out.
Yeah.
So before Newton, nobody really knew physics. Aristotle took a stab at it, and he didn't do so well. But everybody followed Aristotle's geocentric model. But the Greeks, prior to Aristotle, had both heliocentric and geocentric models. There were about 12 different Greeks who entered into this arena, and they all had slightly different models, but they were divided. But Aristotle ruled the day, basically, because he was the chief philosopher. Well, they didn't find his works in Western scholarship until like the 12th century AD. So he was an unknown until then. So, and that's where Thomas Aquinas picked up on Aristotle at that time, made his whole philosophy centered around Aristotle. But the Indians were heavy into this whole thing. Aryabhata in the 5th century AD, and those that followed him, they had about a good dozen models as well, heliocentric and geocentric. Okay. And then you have Copernicus, of course, you had Galileo, you had Kepler, you had Foscarini, all kinds, Nicholas of Cusa, Giordano Bruno, Rheticus, who was Copernicus's friend. They all had, models that were basically heliocentric, but there were variations to them. The reason why you have so many models is because it's easy to make a geocentric model. All you have to have is pencil and paper. And if you can make the geometry work, and so that what we see in the sky matches what's on your paper, it's acceptable. Question is that the true system? Okay. So that's where Newton comes along, because he's the first guy to put things in motion in an equation. Nobody had equations before. Perhaps the closest was Galileo when he rolled a ball down a slide, but he didn't even know how to measure, the Leaning Tower of Pisa balls. He just knew that they both went the same speed. He couldn't put it in an equation for you. So Newton was the first one to put in an equation, and he came up with this equation, the probably most famous equation in the world, and still is today, F equals ma. Force equals mass times acceleration. So when you put that in cosmological terms, what that means is if the Earth is a certain mass, which would be the m of ma, and you have F on the other side of the equation being the gravity of the sun pulling on the Earth, then the A of ma has to be a certain acceleration in order to escape from being pulled in the sun. Okay, very simple. If A is too big, then the Earth is going to go out into outer space. If A is too small, then it's going to fall into the sun anyway. So it has to be just right, which is what, about 20 miles per second, they figured out. So that model seemed to work pretty well. I mean, the sun is bigger. It has 99% of the mass of the solar system. Earth's tiny. Even Jupiter's tiny compared to the sun. So if there's any place that holds the weight, you might say, it's the sun. So, and if you believe that mass causes gravity, well, then the sun's going to pull all these objects in there unless something can take them away. Okay. And the only thing that we know that could take them away is a revolution that's fast enough around the sun. So it seemed like a perfect model. I mean, for the first time, somebody put an equation to motion. I mean, that was stupendous. I mean, if you had to put an equation to Aristotle's understanding of motion, it would be F equals mv. F equals mass times velocity. But,
yeah, I was going to ask you about the acceleration part, because that seems to suggest that something's moving faster and faster as it goes instead of just a static speed.
Exactly. Yeah. Well, the Earth is going the same speed. It's just going around in a circle, and whenever you have a circle, you have acceleration.
So the centrifugal forces are offsetting the gravity of the sun, then, sort of?
Here's the thing. Newton doesn't have any centrifugal forces. Okay, they're all fictitious according to Newton's equation, because F equals ma doesn't say F equals ma plus centrifugal plus Coriolis plus Euler. It just says F equals ma. Okay, so then that begs the question as to, well, where do these centrifugal, what we call inertial forces, how do they come into the whole scheme of things? Well, in Newton, like I said, in Newton's scheme, they don't exist. That's why they're called fictitious. They're just what we call as results of, or what you call artifacts of motion. That's all they are in Newton's system. They're not real in the sense that it's a real force. They're just what you see as the result of other things moving. Okay. Which is going to come back to haunt them later on. Okay. And the reason for that is because in a geocentric system where the universe is rotating around a fixed Earth, you're going to have the inertial forces, centrifugal, Coriolis, and Euler, but they're going to be real forces. So we can tell where they come from. And those real forces are going to force all the celestial bodies to go with the universe as it rotates around the fixed Earth, so that we see them all go around the sky every day. Okay. Because you would have to ask, well, if the Earth is still, what's making those things move? Well, there's real forces making them move. That's generated by a rotating universe. Okay. And that's where Einstein came in. And basically what Einstein said about Newton was, here's the thing with Newton. He only dealt with the solar system. Okay. And made the universe inert. Had no force on the solar system. It was absolute because he wanted to make it infinite. And he made it absolute and couldn't move. And why? Because if you're going to say F equals ma, and if the acceleration of the body is too great, then it's going to go off in a straight line. But in order to have a straight line movement, the background has to be fixed. It can't move. Because if the background is moving at the same time the object is moving, well, then the object's not going to move in a straight line. Okay. And that's where you get into Einstein's curved space. Newton didn't have any curved space. He had absolute space. Everything was straight. Like even Descartes, what do they call that? Cartesian system, can measure because it was all straight. But if it's a geodesic, if it's curved, it's going to be hard to measure that thing, you see. So that's where the relativity comes in. But anyway, Einstein said that Newton's mistake was that he limited his laboratory to the solar system. And you can't do that in science. You just can't arbitrarily have a metaphysical idea that the universe doesn't move, because you don't know that. Okay. It could be that the Earth is fixed and the universe is rotating around it. So you can't make an arbitrary decision before you come into your experiment and say, well, here's what we're going to assume first. Okay. And Mach picked that out first, Ernst Mach, before Einstein. And then Einstein said, yeah, he's right. And then there was a whole slew of physicists who came along and say, yeah, Newton can't assume that as a fact. But if you assume it as a fact, then yes, the Earth has to go around the sun. No questions about it. You have no options. And that's because in the solar system alone, the sun has 99% of the mass. And that's it, period, end of story. Let's move on, talk about, when we're going to go swimming. Because there's no argument after that. So once you say that the universe can move, and it has to move on a daily basis, because we see them go around. We see the stars go around in 24 hours. Okay, now we're in a whole different realm. And at least we now have the possibility that the geocentric system is correct or is viable, because we have the physics to explain it. And that's where general relativity comes in. And Einstein himself admitted that you can say the sun goes around the Earth or the Earth goes around the sun. All you have really is different coordinate systems. And you can have different physics for different coordinate systems, you see. So he made it rather easy for us. So I come along and I see this and I'm saying, oh my gosh, Because I had been gone by Newton all along. I didn't even know Einstein supported the geocentric universe. And most physicists,
I don't think people do. Still, they don't know that.
still they don't know that. Physicists don't know that. If you bring it to their attention and they're worth their salt, then they say, oh, yeah, that's true. But they had to be educated to that first. So all these guys out there, they think that Einstein was a heliocentrist. And yeah, I mean, one part of his theory can support heliocentrism, but in order to be a relativity theory, it's required that you have a reciprocal system that is the mirror image of the one that you brought to the fore first. That's what relativity is all about, because relative motion means
Relative, yeah.
One can move, the other stops. The other can move, and the other one stops. You see, that's what relativity is. So they have to have one, whether they like it or not. And guys like me love that they have to have a geocentric system, because now you want to get to the religion part of it, here it is. Because as a Catholic, I believe that the church is guided by God to give us true doctrine. You know, whether it's about Jesus or the saints, the Pope, the church, whatever it is, they give us true doctrine so that we can live by faith and proper morals. We have to have some source. Catholic Church says it's the main source because what it says is infallible. It's without error, because God wouldn't give us error to live by. Otherwise, he couldn't judge us if we didn't have the truth. And we believe that God is with the church all the time, not just some of the time, guiding her into truth. So when Galileo came on the scene and said, Scripture is wrong, or at least your interpretation of Scripture is wrong, because you think the Scripture says that the earth doesn't move and that the sun is the one going around. Well, he contested that, and the church said, no, you're wrong. We've believed this for 1,600 years, and you're not going to come along, especially without proof, and say, no, we've got it wrong for 1,600 years. Sorry, Galileo, you can become the Pope. You know, that just wasn't going to happen, of course. But the church didn't have proof either. All she knew was Galileo's arguments were, you know, they just weren't arguments the way he was proposing them. And so they were stalemated in that sense. But the church said, look, this is what we believe. We're going to continue to believe it unless you can prove us otherwise. And he couldn't. Now, the one that they thought could prove otherwise was Isaac Newton, because he's the guy, as I just said, used the solar system alone and an equation and showed, yeah, the earth would have to go around the sun. So everybody was like, oh, wow, here it is. Here's the answer. And so, I mean, that was the darkest time for the church, because she had nobody in her corner saying, well, Newton, you know, you're not so hot either, because that didn't come until 200 years later when Ernst Mach came on the scene. So you can imagine what the church was feeling like. We had no proof to go against Isaac Newton, the great Isaac Newton. I mean, Immanuel Kant said he was the greatest scientist ever to come along. And Immanuel Kant was the greatest philosopher ever to come along. So it was like two peas in a pod, you know? So that's basically the story. If you want to get some more details, you can ask me questions, but.
Yeah. I got lots of questions. Darren, do you want to go first, or?
Yeah. So, you said where did you start? Where did you start? This is, what was like the aha moment? What was the something don't fit right here?
That's a great question. The aha moment. I guess it started when I went into the so-called proofs of heliocentric system, like stellar parallax, stellar aberration, the Foucault pendulum, star streaming. Those are the four biggies that they used after Newton to try to prove Newton's case. And then when I saw the geocentric answer to those that nobody had ever shown me, or had I ever seen in a textbook, physics, science textbook, never, ever did I see it. And here I saw it and I go, aha, wow. So the very proofs they were using are now discredited, all of them, especially stellar parallax. I mean, that's an easy one because all they show you is the Earth going around the sun and thus creating a different angle to the star they're looking at. But you could do the same thing with the sun going around the Earth. See, because the sun moves with the stars and it's going to create the same angle that you would get in the heliocentric system. So it's just a matter of which one you prefer. But they can be answered, you see.
Isn't there some problems with the Mars lunar syndonic cycle as well? Like how Kepler averaged that out instead of going with the standard one. That's the stuff Simon was talking about on here. How they just took that and averaged it out.
Well, you would get the same problem in the geocentric system. You see, because there's a lot of anomalies out there with the planets. They don't move in exactly elliptical orbits like Kepler told us. These things are, when you consider that there's, okay, so they took away Pluto. We can't have that as a planet anymore. And they're all having gravitational attraction on one another, and they're all in different places at different times in different centuries. You're going to get some things that are going to happen that you just weren't prepared for, because the most they can do with a computer is like 3 things in motion. And even that's hard. When you try to put 4, 5, 6 things in motion, see how they all affect one another, that's almost, it is impossible. They can't do it. So they come up with these things that they see, whether it's Mars, Saturn. Saturn's got big problems out there. Okay. And I mean, for like a few days, it looks like it's not moving. It's like, where's that coming from? And but we would have the same problems in the geocentric system. So we don't claim that we've answered all the questions. We've just answered the big question.
Well, maybe since we're still on, since we talked about Simon's, do you want to mention some of the things that you like, some of the stuff that you and Simon sort of agree on, and then some of the stuff that you don't? Maybe some of the reasons why you think Simon's model isn't correct.
Yeah, I have to be honest. I don't think Simon's model is correct. Okay. Like I said in the beginning, if you have a pencil and paper, you can sit down and figure out any kind of geometric system and sort of make it work. That's why you have so many different geometric style models, from Pythagoras at 600 BC to Kepler in 1500 AD, because it's easy to make a geocentric model. And Simon has made one of those. It's a little weird, I think, but it might be viable in the sense that if you put Mars here, then you got to put Sirius here, and you got to put Earth here, and the Earth has to move a little bit, and you can make that work. But again, whether that's the right system or not, that's a whole different ballgame. So you take more the Earth moving. My model is the Earth does not move. Okay, doesn't rotate or revolve. Simon has it moving like Crombit had it moving
a mile per hour or something.
Yeah, and I think, as I said, that's to accommodate the positive result of the Michelson-Morley experiment. I don't know, because that's what Crombit did. But at any rate, mine doesn't move, doesn't rotate, doesn't revolve, and that's because it's the center of mass for the universe. And by definition, a center of mass doesn't move, okay, unless the whole system moves. The whole system moves and the center of mass will move with it. But as a definition, inside a non-moving container, there's one center of mass and it doesn't move. So that's where I'm coming from in my model.
How does that explain the wandering of the North Star back and forth between Vega and Polaris on the
Okay.
every 13,000 years?
Yeah, every 13,000. So what happens is if you have a universe that's got more matter on one side than the other, and they have found that now. They have in studies, recent studies, just like last year, they have found this, that there is, if you take a ratio of the galaxies in the universe, it would be like 51-49. So we have a lopsided universe, not like really lopsided, but slightly lopsided, so that what's going to happen when it rotates around a fixed Earth is it's going to precess. That's what you're going to get when you have either a force that's going to affect the system, or you have a lopsided, overweighted system, and you're making it rotate. It's going to precess. So that precession, there's actually three of them that you're going to get when you have a lopsided universe. One of them is the 26,000 year precession, which means it's going to go to Vega and come back to Polaris in 26,000 years, okay? Because the axis is itself rotating because of that precession. So that's how we would explain it.
Okay. I think the hard part for me is not, and leaving the scientific part out of it, just that kind of had it ingrained in me for my whole life that, that obviously that the sun, we go around the sun, and that there's all these other stars and everything goes around and all these different galaxies. So saying the universe is hard, right? The Earth is the center of the universe is a tough swallow, right? It's like, because it just throws all this other stuff at me. I love the stuff about like the solar system not working as we thought. Like, I feel like I'm more open to that from a non-scientific view, just a I don't know, a cultural view or something, but it's that whole universe thing. Like, what does that have implications for all these other things that we've talked about?
Like what? You have to draw that out for me a little bit, because I'm not following.
Well, what about all the other planets that we see out there? Like, how does that implicate like the mainstream narrative of space, the planets, the moons that are going around, like all that? Like, does that mean there's not life on any other planet? What are the planets then? If we're the center, like, what are all the other planets, and why are we the center, and why are we so special? I know there's some cliche questions in there, but like, it just feels like too special for me. Like, I feel like we should be just one of the planets that has life.
Yeah, well, a guy from my perspective can answer that pretty easily, because I come from also the religion perspective. And the religion perspective says that we are special.
Yeah.
And God made us special. He made us in his image. And what can show that you're more special than being in the center of the whole universe? Okay.
Yeah. Well, yeah.
As a matter of fact, this is what the scientists don't like. Why they don't like geocentrism, because it smacks too much of God, you see, because they know that if the universe is in the center of the universe, it ain't going to get there by time and chance. They know that, you see. So instinctively, they resist it. They would much rather have the Earth out in the remote recesses of space with no signpost saying, here you are, because that's more comfortable, because that we can imagine coming by time and chance without a God.
Yeah, I totally agree. So what about all the the voyages out to other planets like the Mars, all the the spaceships that have gone to Mars and come back with samples, or what? Like, is that all like where do you like where does this fit with all the stuff in our solar system?
I'm not sure where you're coming from, but it's not going to change anything. I mean, they haven't found life on Mars or Pluto or any other place. Okay. And the odds of finding, even according to them.
Well, I mean, they just said they found water on one of the moons, for example. Like,
there's water in the whole universe.
Yeah.
I mean, it's amazing how much water there is out there.
So is there life in the universe then, according to your? Yeah.
Well, water is not life. Water is H2O.
No, but is there life too, though, or?
No, I would say no.
Okay.
Yeah. But there's a lot of water. There's even water in the sun. and the sunspots. Yeah, believe it or not, 3,500 degrees Fahrenheit. There's even water in the sun. There's water in the stars. There's water in the planets. They just found Pluto. Almost the whole surface is water in ice form. Pluto has mountains made of ice, and they have volcanoes that flow out water. Okay. So, I mean, there's water everywhere. It's one of the building blocks of life. As a matter of fact, there's so much water out there now that they've discovered that they think the water molecule is the actual fundamental basis of existence instead of carbon, even if you're talking about life, because they've seen it everywhere. So, yeah. So but see, we can answer that from a biblical basis, because it says in the beginning, in Genesis chapter 1, in the beginning, God created the heavens and the earth was formless and void, and darkness was upon the face of the deep. Now, there you have it. You have the earth created first, covered by the deep, and that's a Hebrew word for water. Okay? And it's a lot of water. You got this big ball of ice that envelops this little tiny sea, the earth, and that's where the whole water comes from for the universe. That's what we understand it. And that ice has to be melted, which is melted by the light, because it says, and God said, let there be light, and there was light. And there's your heat to melt the ice. And once that heat melts the ice, then the pressure's taken off, and that thing just explodes out and makes a universe, basically. And that's why water is out in the universe. So, we have an explanation for that.
I was going to mention too, when you said that that's what the scientists have a problem with. There's also another kind of problem or conundrum with the science and the floods, and I think there's been resistance of the mainstream science to embrace a grand sort of flood theory because of the Bible, because they don't want to admit that there's been a massive flood, because of what the Bible says. Like even, guys like Randall Carlson that have been sort of catastrophists and talk about these massive floods, like either global or North American or whatever, but they want to just they will use, Catholic and religion to try and debunk or to disparage his research, because they're also resistant to like an ancient lost civilization, or a civilization that was older than 6,000 years and was destroyed by a massive flood, which kind of like half matches the Bible, I would say.
Yeah. So I mean, that's a whole other subject, the flood theory, and I deal with that as well. But let me give you some food for thought on this geocentric issue, because the data is the data. The data is neutral. But when a man goes and looks at the data with his telescope or his microscope or his oscilloscope, whatever scope he uses, he has to interpret the data. And whether he likes it or not, whether he will admit it or not, he is influenced by his society, by his theology. Everything influences his interpretation of that neutral data. Okay, now I'm going to give you a perfect example of that in the geocentric issue. So there's this guy named Edwin Hubble. I'm sure you've heard of him.
Oh,
right?
yeah. I wanted to ask you this too. I'm glad you're mentioning it. Yeah.
Yeah. It's one of my favorite stories, because it just shows you what's going on. So they built this great telescope out in California, the Mount Wilson telescope, that was 100 inches wide. I mean, that was big. It's the biggest one we had in the world. And so Edwin Hubble, the greatest astronomer at that time, they let him go use it, and he sees galaxies.
Back in the 20s, right? 1920s? So 100 years ago, right?
1929, almost 100 years ago. And he sees galaxies for the first time in human history. They were theorized, they were thought of, but nobody saw one, and he saw one. Not only did he see one, he saw, millions of them. And he noticed something very peculiar about them. And that was that, except for a few, and we can explain why just a few, because the Andromeda galaxy wouldn't fit in there because it's too close to us.
Too close, yeah.
But all these other galaxies are far away, and the light from each of these galaxies showed a redshift. Every single galaxy that he looked at. Now, he, as an astronomer, knows what causes redshift. Either the emitting object is moving away from the observer, could be gravity on the light, but that's what causes a redshift. And he said, well, if we weren't in the center of the universe, then we would see blue shifts as well as red shifts, you see. But we don't see any. We don't see any blue shifts. We see red shifts. So his conclusion was, wow, this puts us in the center of the universe. Okay. And you can read about this in his 1937 book, The Observational Approach to Cosmology. And he's playing for the scientist. He's speaking for them. And he says, now, what do we do with this situation? Because we don't like this, that the evidence puts the earth in the center of the universe. So and he uses words like, this is horrible, this is unacceptable, we will only resort to a central earth as a last resort. He just goes on and on for like 6 pages. He's like he's having a mental breakdown. So he says, how do we get out of this? So he thinks up a theory. And he says, all right, this is what we'll do. We'll dispense with Euclidean geometry that has a center, and we'll just use Riemannian geometry that has no center. It just has 2 dimensions. And the 2 dimensions put it into the shape of a balloon. And so what we'll do, we'll take all these galaxies and we'll put them on the surface of the balloon, and then we'll blow up the balloon, let it expand. And as it expands, the galaxies are going to move away from one another, right? And guess what they're going to see? They're going to see redshift. So every single galaxy out there, because it's on the surface of a blown up balloon, is going to see redshift. And voila, we have our answer to redshift.
And is that how they came up with the expanding universe theory too?
That's exactly how they came up with it.
So, oh man, and they probably said, they didn't make him an offer like, we'll just play ball and we'll name a space station after you in the future? Or?
Well, here's the interesting story. He had a partner named Humason. And Humason said, you can't do that. You just can't assume that the universe is a balloon, put the galaxies on there to create redshift so you can have an answer for the earth that's in the center. You can't do that. And he left him.
Wow.
And Hubble started to equivocate. One paper he would say, yeah, I accept. Another paper he'd say, well, not so. So he didn't know where to move. But they probably gave him enough money, prestige, and the name on the telescope. Who knows?
Yeah.
I mean, because this is what life is about.
Yeah.
Just take a look at our politics. I mean, if we don't know that now, we'll never know it.
Yeah.
Okay. But you think that science is immune from that? Are you kidding?
No. We've seen how corrupt it is now, especially over the last little while.
So this is another, to answer your question, Darren, another aha moment I had. Okay. You mean this whole Big Bang theory is just to get away from the central universe, or central Earth? Yeah. And then another guy comes along, he was a Catholic, liberal Catholic, which means he didn't believe the Bible or didn't, trust anything else. Father Lemaitre, Belgian, mathematician. He says, okay, we got an idea. Let's do this. Let's take this blown up universe and shrink it down. Let's make it go backwards. Okay. And you get down to what? You get down to a little seed. Okay. And then here's where the debate started about, well, what was this little seed and where did it come from? And, then they use words like singularity, which doesn't mean anything. It just means it's a single spot that I can't explain is what it means. And so you get this Big Bang thing because the seed exploded somehow. and made the universe expand. But the key to all this is, where did the Big Bang Theory come from? It came from a guy who didn't want the Earth in the center of the universe.
Yeah. So there's a couple great comments in the chat that I don't want to leave past, but Corey Ash says, because I was thinking about this too. I was actually looking up the definition, because your name is very ironic in a way for a geocentrist. Sungenis, is like he's meant to do this work, And then Jerry says he saw you on the Culture War about flat Earth. You were great. I saw a little bit of that, but were you on there, just for people, were you on there debating the flat Earth, or where does your theory fit with the flat Earth? Like,
well, we don't believe in a flat Earth, that's for sure. But I was asked to write a book, well, actually a paper, back in 2018. I was asked by another organization to write a paper on this flat Earth theory, because they were being bombarded with people asking about flat Earth. So I started the paper. I wrote 30 some pages. And then as I really started to get into it, I go, oh my gosh, this thing it's like a rabbit hole. Once you go down it, they come up with all kinds of things, and they all have to be answered. Because if you leave out one, you're like, see, gotcha. Can't answer that one. The Earth is flat. So I made sure I answered all of them. And the book ended up being 735 pages long, called Flat Earth, Flat Wrong. So that's what I use, is spherical Earth, and I think it makes the most sense. And the guys that don't believe it are like, they don't believe in satellites. Rob Skiba was one of their top spokesmen, and he remember I said, Rob, and he seemed like a sensible guy. He died a few years ago. I said, Rob, do you really not believe in satellites? That NASA's just lying about all these things?
And yeah, that's kind of why I was asking you those other questions before. I wasn't sure if this fits in with any of that. Those are sort of extreme space conspiracies, I would call them.
Yeah.
What did he say?
He told me in private. He says, I do believe in satellites.
Ugh.
And then he died the next year.
Wow.
Yeah. So it's like, wow, what do I make of that? But he did say that he believed in satellites. And that just sort of begged the question, because the next question would be, well, why don't you believe that these satellites show a spherical Earth? We didn't get that far.
Yeah.
Believe it or not.
Apparently, that's a deep rabbit hole on its own. The chat saying that the deep state took him out.
The deep state no, he died of COVID ramifications. No, well, maybe that is the deep state. Who knows?
Yeah. That's a good.
We're wandering into YouTube strike territory here.
Oh yeah, that's right. Yeah.
Ixnay and the
Thank you, Derek.
vaccine.
Yeah.
So how does this because I don't know where I'm still sort of absorbing some of this, because the interesting thing is,
let me give you another story if you'll call it from the here. Let me give you
let's do it.
This is about Albert Einstein himself, because he wasn't always allowing a geocentric universe. He had to come to that by force. And I'll tell you,
nice pun. Yeah.
Yeah. So they did experiments in the 1800s, 3 famous experiments. Dominique Arago in the 1810s, George Bedell Airy in 1871, and Michelson Morley in 1887 and 1897. And each of those experiments showed that the Earth could be fixed in the universe and not moving. Okay. They were all experiments based on light, how light moves. And after the 1887 Michelson Morley experiment, these guys were scratching their, how are we going to answer this experiment? We've got to have some way to explain it. Otherwise, we're all going to be kissing the feet of the Pope for condemning Galileo's heliocentric universe. Okay. Because if the Earth isn't moving, that means there ain't no Big Bang. There ain't no, a lot of things. And they didn't like that. So
Well, I guess technically there could be a Big Bang. We would just be at the center of it.
Well, that's not what they think. I mean, they think the Earth was made 8.5 billion years after the Big Bang.
Yeah.
So that doesn't help us. At any rate,
because we kind of described a Big Bang. It's just like the Earth was the cause of it in some ways. Like the light melted the ice and the Earth expelled out all the.
Well, yeah. I mean, you can have an expansion because the Bible is replete with references to God spread out the heavens. He stretched out the heavens. There's 12 verses in Scripture that say that. So it must be an important topic because you have to figure if you make the Earth first, well, how are you going to get to this gargantuan universe? Well, something's got to move, right? So that's what happens. But anyway, getting back to the Einstein thing. So they're scratching their head. 25 years later, Einstein comes up with an idea. Here's how we'll do it. We'll make the speed of light constant. And according to the way this experiment works, that means the Earth has to move. Now, that was a postulate. He didn't prove that the speed of light was constant. That was just something he had to assume in order to get out of this conundrum that the Earth wasn't moving. So he had two choices. Either the speed of light's constant or the Earth is constant. That is, it doesn't move. Which one do you think he's going to choose? Okay.
Well, that hasn't really aged well either as a theory, has it? I mean, because aren't they kind of going, nothing can go faster than the speed of light, but then stuff's going faster than the speed of light.
Yeah, I mean, it becomes a big joke, okay, that nobody wants to admit the emperor doesn't have clothes on, okay? How long is it going to take them to come to that point? And this is exactly what happened when 10 years later, Einstein says, oh my gosh, the special theory of relativity, which says the speed of light isn't constant, isn't working because light is affected by gravity. Fast or slow, it's affected by gravity and inertial forces. And the universe is filled with gravity. So how are we going to have a special theory of relativity work in the real universe that has forces all over the place? And so he had to come up with another theory to accommodate that or to answer that problem. And he came up with this thing called the general relativity theory in 1915, exactly 10 years after he invented the special relativity to try to keep the Earth moving. And the general relativity says this. The general relativity says speed of light is not constant. It can go any speed. It can go any speed because of how it is affected by forces like gravity. Okay. The other thing is Einstein got rid of the ether in the special relativity. That was the medium everybody thought the light was traveling through. Why did he get rid of the ether? Well, because if you get rid of the ether, that means light doesn't have any obstacle to go through. It just goes through empty space, and therefore it's going to have a constant speed. Oh, well, that makes sense. But he just did a hand wave and got the ether out. He didn't prove that space didn't have ether. He just said, we got to get rid of the ether. And somebody says, well, you can't do that. Well, yes, I can. Or would you like the Earth to be fixed in the center and go kiss the feet of the Pope? Tell me which one you would like. Because I can make either one of them work. So anyway, the general theory, and the general theory also allows material objects to go any speed. Okay, not just light, material objects, you and me, my bookcase back there can go faster than light. Why? Well, because general relativity must have a reciprocal answer to the heliocentric system, but the geocentric system, which is the reciprocal answer, says that the universe is rotating way beyond the speed of light. Otherwise, it wouldn't be able to complete its revolution in 24 hours. Okay, so he has to allow light and material objects to go faster than light in the general theory. Okay, so do you hear anybody talking about that today?
No.
There's a contradiction between special relativity and general relativity. No, it's just seamless. It's just seamless according to them. You see? So
then the speed of a light would just accelerate the further you get from the Earth.
exactly, because you're going to have more inertial forces in a rotating universe the farther you are from the Earth. The more inertial force, the more the light's going to be affected. So the light speed is going to be way higher out there at the rim of the universe than it is here. Here, the terrestrial speed of light would be 300,000 kilometers per second. And even around Mars or Jupiter, it would be, because there's hardly any inertial forces out there. But when you get way out there to the the limits of the universe, you're talking about tremendous inertial forces out there.
Interesting. Like I say, I have come around to I've become a geocentrist as of late. So I'm not as far off as I would have been, maybe say 5 or 10 years ago. Now, I even went to the brink of flat Earth and back, and then I couldn't do it. I started going.
Somebody's watching out for you, Darren.
Yeah, I started going through all the flat Earth stuff, and I was like, nah, this ain't resonating with me. But I gotta say, the Simon Shack stuff really did, especially with the mile, and because the mile does seem to have this sacred connection with all of the, throughout history. I mean, England's still using the mile, for fuck's sakes. They're like the most metric place in the world, and they're still using this mile for some reason.
SNL did a skit on that, of discovering America, and they were deciding whether they were going to use the imperial system or the metric system. And they just made a real funny skit of it. I saw it last Saturday. It was just amazing. If you can, go watch it on the YouTube. You would appreciate it, Darren.
Yeah, well, because it does mix in with this because the other thing that I've come to terms with over the life of the show is that we're dealing with intelligent design on some level. When you see these sacred numbers and these sequences and these, just the way that everything seems to work, it seems like we're dealing with intelligent design. Now, like, I still haven't decided who the designer is, because I think intelligent design still leaves some room even for me to maybe do some design. But I'm coming around to the whole thing.
Well, just be careful. It's a minefield out there.
Yeah, the stuff on the outer limit must be moving. I mean, I'll go to a comment here in the chats from our buddy Mike down in Montana. Mike Wykes. He says Dayton. Now, for a little context, when I traveled to England to go to the Tycho's conference and meet Simon. I mean, it wasn't much of a conference. There was only a couple dozen of us, but I was able to meet him there and get a signed book and see him do his presentation. And Mike went, he says Einstein equals math magic. So he was over at the time. So he's a big Tycho's proponent. So I'm assuming that's where he's coming from with his commentary. But he says Dayton Miller performed over 326,000 turns of interferometer with 16 readings in each one, more than 5.2 million measurements. They showed what appeared to be a small amount of drift, about 9 kilometers a second.
Yeah.
I don't know what
that's true. Actually, it was 8 kilometers per second, but it's true. But every other Michelson-Morley type experiment, and that's what Dayton Miller did. He did a Michelson-Morley type experiment. Nothing was really different from those two experiments. Miller just did a lot more of them than anybody else. He did it from he worked with Morley in 1904, and then he went on his own. And from 1908, I think it was, till 1924 or so, Dayton Miller did all these experiments, because he was convinced that Einstein was wrong in saying that there wasn't any ether, because he kept coming up with a positive result. But all the other Michelson type experiments, and there were 11 others, because there were 12 people who have done these experiments from 1881 to 1930. Jews, Joos, was the last one in 1930 to do it. But you had Kennedy Thorndike, you had all kinds of people doing this. and they all tried to twist it a little bit to make sure everything was just right. Maybe that's why we're not showing the Earth going around the sun. So they tried to tweak it, and but they all had a positive result. And so Einstein, on that count alone, would have been wrong for saying there was no ether, because they knew they all had a positive result, but it was too small. It was too small for the Earth to be going around the sun at 20 miles per second. Okay. They could only get like 1/10 of what they needed for Earth revolving around the sun. And so they were all puzzled about this positive result. And so was Dayton Miller. Okay. But he kept finding a positive result. So that's what we get from him. Positive result. Now, here's the interesting thing. In 1925, Michelson, same guy that was in 1887. So let me do this. Let me stop trying to measure the Earth going around the sun. Let me try to measure the rotation, okay, of the Earth, and see what I come up with. And I'll use the same experimental apparatus that I used in 1887, because it's interferometry. You're measuring the effect of the environment on light waves. So he used the same setup, put it in a different orientation, so that it would measure the rotation instead of the so-called revolution. Okay. Now, here's the thing. Guess what he came up with? Are you guys following me?
Yeah. I can't guess it though.
Guess what he came up with? Almost 100% of ether in his experiment on rotation. In other words, there was enough ether that he could say without a doubt that something's rotating against something else. Okay. Now, he assumed that it was the Earth rotating against space. Now, Michelson Morley, the one that tried to find evidence that the Earth was going around the sun, not rotating, couldn't hardly come up with anything. They came up with Dayton Miller's, the highest was 8 kilometers per second, but they needed 30 kilometers per second. And nobody could get even close to that. But Michelson did one experiment to show rotation. He comes up with a 98.6% positive. Okay. So what does that tell you? That tell you that there's a rotation, but there ain't no revolution.
Huh.
If you just accept the experimental empirical evidence, that's what it tells you. But see, the heliocentrists can't have that, because they need a revolution and a rotation. And if they don't have that in the empirical evidence, then their theory is falsified.
Another reason why they got rid of the ether?
They tried, but they weren't successful. Because quantum mechanics came along at the same time and said, there is ether out there, buddy.
Yeah,
so
but for all intents and purposes, they got rid of it. I mean,
well, they try to pull the wool over our eyes. Yeah. Okay. Yeah. So nobody, guess what? The Michelson experiment, 1925, found 100% rotation rate. Nobody ever repeated it again. Nobody ever talked about it. There was one article written in the New York Times, and that was it. Over. Period. Done with. Okay. Because we can't have this. Okay. So this is another indication of the human mind behind the interpretation. Now, the geocentrists can explain this. Why? Because the geocentrics doesn't need a revolution of the Earth around the sun, obviously. But the rotation, they can explain by the universe going around a fixed Earth. Problem solved. End of story.
The interesting thing about 9 kilometers a second is that would have been 12,960 kilometers an hour, which would have been half of a great year.
Yeah, that's right. But see, it's not horseshoes we're playing. This is, you can't be close. You have to be exact.
What, so before we start to wrap up, so I guess that puts because there does seem to be all these sacred sort of numbers, these building blocks, these patterns, and I guess from your point of view, then that sort of stuff would just be coming from that because it's divine.
Yeah, I mean, I think we've seen by looking through our telescopes and microscopes enough that the constants that we have are truly constant and can't be anything else. Well, there's about 20 of them that if they're off by just a smidgen, we don't have any life, And so that can only give evidence for a creator, because only a creator who has an infinite mind can put all that together and make it work. I certainly can't do it. Nobody else can. So, I mean, here we are.
How long ago was that? I mean, do we have time to just touch on the age of the Earth without going into a whole other
Yeah,
episode?
we can show by using science itself that the age of the Earth is no more than 7,000 years. Now, I can prove it to you. If let's say the average age for Homo sapiens, according to the evolutionary theory, is 200,000 years or 300,000, somewhere around there. Okay. So let's say you start with two people in the year 300,000. We'll just take that as the figure. And then you watch the population grow. Now, in population growth, they have a thing called the T factor. The T factor could be like 50 on the average, or could be as low as 30 in some instances, but it's around 50, 60, 70. Okay. What that means is every 50 years, the population doubles. Okay. Or every 60 years, the population doubles. So let's say you give them 100 years for the population to double, and you start at 300,000, the year 300,000 BC, with just two people. And this includes sickness, death, anything that can happen. The T value includes all of that. So it's all been thought out before. Okay.
So cataclysms and all that kind of stuff.
Yeah, everything. You put it all in there in the mix, and usually come out with 50 years as the doubling of the population. But we're going to give them 100. Okay. Guess what happens? By the year 293,000, you have 2 trillion people on the earth. Okay. And we're using their rules. The T value is their rule. Okay. It's 2 trillion people in 7,000 years. Okay. If that's the case, well, then can you imagine what's going to happen in 200,000 BC? How many we're going to have? And if that's the case, where are all the bones? We don't find them underground like that. We find here and there.
What about some of the? Yeah, I mean that's interesting. The human part, but what about the physical stonework that we see that seems to be older than 7,000 years?
Well, because they're making assumptions.
Yeah,
They don't want
the dating of these things.
I can tell you that. That's why, for example, they won't do carbon-14 tests on Tyrannosaurus Rex bones that have soft tissue. Why? They won't do it because they know it's not going to be 70 million years. Carbon-14 doesn't even go out that far anyway, but they know they're going to get around 20,000, 10,000. That's what the results show if you do the carbon-14 test. So they're already fixed on. Did you ever read that story of Mary Schweitzer, who found the T-Rex soft tissue because they broke the bone accidentally, and they found soft tissue, blood vessels, blood cells, collagen, okay, inside the dinosaur bone that's supposed to be 70 million years old. And she took it back to her, I think it was University of Colorado. His name was Jack Horner, her boss. And he said, well, what do you got here? She goes, well, it looks like we have soft tissue and it's organic. And, I can verify all this. And he goes, you know what his next words were? Show me that it's not.
Yeah. Yeah. Interesting. Wow.
Yeah.
So is the rest of the timeline kind of fit from present to 7,000 years ago? Because that kind of scrunches everything up in some ways, or changes
for the big bangers, it does scrunch it up. Yeah. Okay. But see, they want time. Time is their little crutch.
Yeah.
Give it enough time, And these monkeys will spit out Macbeth from Shakespeare. Just give it enough time, you see. And that's how they live. Time and chance.
Darren, got anything on that?
No, I mean, it's some stuff to get. I'm gonna have to read some of your books now, I think. Where can people find those books?
You can go to journey to the center of the universe.com.
Are any of them available on audio?
What's that?
Are any of them available on audio?
Audio. Let me think. Do we have anything on?
It looks like you have MP3s on your website. I don't know if those
Oh,
are
yeah, we do. We have MP3s. Some of them are science. Most of them are theology and Bible stuff. So, yeah, but just search the website. You'll find something. I would suggest, if you're just starting out on this road, Geocentrism 101 is probably the premier book to go to. And then we also made a movie. I don't know if you guys know about this. In 2014, called The Principle.
Okay.
This was a theatrical release. I was the executive producer.
Cool.
And we had some of the top scientists in the world in that movie. Okay, like, let me see, who would you know? Michio Kaku. You know Michio Kaku?
Yeah.
He was in our movie. Max Tegmark was in our movie. George Ellis was in our movie. Few other names you might be familiar with. And guess who was our narrator? Our narrator was Kate Mulgrew, who was Captain Janeway on Star Trek, on the Star Trek show,
Cool.
1975. Yeah, so, and she's got a great voice. So that's called The Principle, and it covers a lot of what I covered here, only in an hour and a half, because it was a theatrical release.
How can people get that?
Go to the same website. It'll be right there, called The Principle. Yeah.
All right. Awesome.
Great.
Okay.
Yeah, this has been great. Robert, we appreciate you coming on the show. You mentioned the website. Do you have any social media or anything like that where people can track you down or follow your work?
Oh, gosh. I'm very rarely on Facebook. I try to stay off of it because it's just a time sucker, you know. I just can't afford it. But I do have a Facebook page, you know. Yeah, that's all I can tell you.
Okay.
Okay.
All right.
Great.
We'll put a link to that in the show notes. Thanks.
My pleasure. Thank you.
It's been great.
All right.
Come back anytime.
Okay. You have to do the inviting. I can't invite myself. So.
Okay, no problem.
Take care.
As the first one to ever call me on that. Big thanks to Dr. Robert Sungenis,
Sungenis, I think. Yeah.
Sungenis for coming on the show. Big thanks for you guys for listening, for tuning in live and asking some great questions. I mean, Mike had some more, but I didn't want to keep going with it. So
it's funny. Mike was here. I'm glad he showed up.
Mike Wikes. Yeah, good to see him in the chat. So big thanks to Robert for coming on the show. Big thanks to you guys for listening. Even bigger thanks if you're one of our nobles. People have to choose to support us and keep us on the air over at grimerica.ca/support. We don't get any money from YouTube or anyone else. So you got to just support us yourself at grimerica.ca/support. If we're the kind of content you want to see more of on the internet, you can also head over to grimericaoutlawed.ca. Check out our other podcast over there. Head over to contact@thecavern.com for the trips. And adultbrain.ca for the audiobooks. And, of course, Grimerica CBD for our new CBD products, which is great. I mean, you got to check them out. Check it all out. All that stuff also supports us. But the best way is head over to grimerica.ca/support and start with that, even if it's just a couple bucks a month. So there you have it, guys. We love you. Thanks for listening, and we will see you next week.